it's all over YouTube. Everyone's talking about the speed of light, can it be broken, blah, blah. It was in answer to Sabine Hassenfelder's video about whether the speed of light could be broken. She said she thought it could. I disagreed in my video. I thought matter wouldn't survive it, and I went through a few things, and the video is probably worth watching. But that's not what this video is about. This is about the experiment that would actually do it. And so I ran the numbers, and I got this number off of YouTube. Somebody said the fastest a proton could go was, well, it's got a bunch of nines, basically 29s and an 8, 0.9999998. And, well, I don't know how they got that. I don't know where that happened. That's very fast. But I calculated a much lower number that I would need to make this experiment successful. Now, the problem is getting that last little bit. You're closer and closer to the speed of light. The object you're trying to accelerate is increasing in mass. So I need a form of propulsion which is going to work irregardless of mass, or regardless of mass. And it's going to work no matter how fast the thing is already going. It's got to accelerate it even more. Well, that's gravity. Now, I started thinking about where the suitable spot would be. A neutron star is too far away. We can't get there. So the next best thing, the sun's too hot to deal with, to get close to, and too weak if you get far away. And so I picked Jupiter. Well, I didn't have much of a shopping list, but Jupiter has an escape velocity of 210,000 meters per second. But that's not really relevant because we can't capture it because we're going too fast in the first place. We're going to have to use an accelerator. And this accelerator is going to have to go up there in a rocket ship. And so we're going to accelerate, I say, protons, because you can grab them because they're charged and they're massive. Electrons are another choice, but I picked protons. So here's how the numbers work. We want to accelerate this proton to, well, I just picked a number I could work with, 0.9999997. And now, according to what I've been able to find, that is quite reachable. This puts it within 9 meters per second of the speed of light. Gravity on Jupiter is like 30 times what the Earth is, but it's bigger too. I mean, it's heavier, but it's bigger. So if it was heavier and the same size, that'd be great, but it's not. So, and I don't want to go all the way to the surface. So I figured you go to within about 4 radii of Jupiter. And you launch these protons down there, and at that point, well, no, let me do it a different way. Let me say you launch them a light second away, and that's 186,000 miles. Now, I don't know the mean free path of a proton in space, and I figure if you go in front of the orbit of Jupiter, then you got closing speed, which who cares, because the speed of light is so much more anyway. So Jupiter wouldn't be moving very much during the time that your proton's going to hit it. But we're not going to hit Jupiter. What we're going to do is launch from a light second away, and that light second should get us at least 20 meters per second additional speed if you're not getting too close to Jupiter. I don't want to get close to the atmosphere. So that puts it over. That puts it over, and it does not matter how much those protons gain in mass, because all masses fall at the same speed. Hey, if it goes to infinite mass, the better the party, and that would pull Jupiter out of its orbit. I suggest that is not going to happen. I think, well, I don't really have a prediction about what would happen, but I got a wild guess. And my guess is the matter would not survive it, and then matter in its parts weighs a whole lot less than it does, and it would scatter all different directions. And it basically, I think it might create a large flash, because the fields would then have to catch up to the matter that started the fields. We'd be breaking a barrier. I don't know if that is possible. I only know the way to achieve it experimentally. So there you have it. Now, I don't have the equipment to do this, Elon. All you need is a couple rockets. One of them's got the accelerator. Oh, okay, it's got to be big. But, as I say, it does not have to accelerate to the limit that they say you can accelerate a proton to. It's only got to accelerate it to what I said it was. Then I would suggest an observation vehicle. And that observation vehicle will be at the expected spot of the breaking of the speed of light, which would be about half of a Jupiter radius above Jupiter. Or maybe a quarter, whatever you can get away with. Okay, let's do that. A quarter of a radius up from Jupiter. That's our target. But, hey, our target doesn't matter because we're releasing the thing a light second away. We want to get the whole second if we can. 3/4 of a second's fine, because we're talking about, we only have to go another 10 meters per second. And I think, and at the surface, we're looking at 30 meters per second squared. And so one radius up, well, it's tough. And that's why I say we're only going to be able to get a second. Now, if you could release the thing 2 light seconds away, well, it doesn't matter, because until you get close, until you get within 4 or 5 radii, the gravity's not going to be good for much. But that is the way to break the speed of light. Who's going to do it? Elon Musk?